The Science Wars and the Goal of Comprehension. All's fair in love and war. One of the few wild ideas that I've never seriously entertained is the notion that certain aspects of reality are inherently incomprehensible. As difficult as the subject matter of quantum mechanics is, I have found it at least as difficult to understand why it is that pessimism has been adopted as the standard intellectual stance in this domain. Because I understand concepts as the tools that we develop and use in order to make sense out of our experiences, I assume that we could always develop better concepts or use our existing concepts more effectively. Quote, "The best that most of us can hope to achieve in physics is simply to misunderstand at a deeper level." Wolfgang Pauli. If what we accept as true also doesn't make sense to us, then this must mean that either the concepts themselves, or the way in which we apply them, or both, must be inadequate in some respect. Before we give up on making sense out of reality, it would be a good idea to take the time to critically assess both the concepts that we have at our disposal and the ways in which we use them. I am confident that there is a way out of this cognitive labyrinth, and my nose tells me that there's a block of cheese waiting for us at the exit. Quote, "If you think that you understand quantum mechanics, then you don't understand quantum mechanics." Richard Feynman. Under the assumption that we share the common goal of increasing the breadth and depth of our comprehension of reality, then it is possible to evaluate our conceptual evolution by reference to this goal. Through a comprehensive examination of the history, the function, and the structure of our concepts, we can determine whether the advance of time has brought us closer to or further away from this abstract goal that we call truth. The way forward should also be illuminated through engaging in this analytical exercise. Quote, "If you can't explain it to a 6-year-old, you don't understand it yourself." Albert Einstein. In a myopic spurt of caffeine-inspired optimism, the Age of Enlightenment brought with it the idea that truth can be obtained, refined, and tamed, and that subjectivity should be replaced with objective knowledge. More recently, in a cynical cloud of cannabis-induced nihilism, postmodernists have wholly abandoned the pursuit of truth. While modernism often fails to appreciate how elusive, dynamic, and destructive truth can be, postmodernism doesn't show any interest in truth. Even the desire to acquire an accurate interpretation of reality is viewed as both foolish and arrogant under the postmodern ethos. Science is regarded as mere role-play. Science is pretend. Climbing and maintaining the social ladder are the real goals, and enlightenment is just a myth. Quote, "Young man, in mathematics, you don't understand things. You just get used to them." John von Neumann. Modernism and postmodernism are diametrically opposed to one another, but each school of thought has some guidance to offer us in our pursuit of truth and understanding. The best ethical inclination that we can keep from the Age of Enlightenment is the idea that it is both noble and virtuous to pursue and to promote truth, and that science and rationality can and should progressively bring human thought into alignment with objective truth. Postmodern thought can also provide us with a humble appreciation of subjectivity and ambiguity, an awareness that there are multiple paths to truth, the idea that these paths are winding and littered with obstacles, a healthy skepticism towards authorities and institutions, and an acceptance of the fact that the pursuit of truth is perpetual. Quote, "If I have difficulty with quantum theory, and I do, it's not for want of trying, and certainly not a source of pride." Richard Dawkins. Both modernists and postmodernists do speak nonsense, but there is an important difference between the two. A true postmodernist would not suffer the slightest hint of embarrassment upon having their statements exposed as nonsense. But in the same situation, a true modernist would be mortified. Again, I find that it is optimal to integrate aspects from both approaches. Speaking nonsense is something that modernists correctly identify as problematic. But we can also acknowledge, as the postmodernists do, that speaking nonsense is quite common and that it does seem to be inevitable to a degree. When it comes to speaking nonsense, we need to maintain our sense of humor and find the balance between punitive and permissive attitudes, so that we can successfully reduce the noise. Speaking nonsense is only shameful when it is done deliberately or either out of negligence or willful blindness. Quote, "It is wrong to think that the task of physics is to find out how nature is. Physics concerns what we say about nature." Niels Bohr. It is easier to stay on track if we think of truth as a direction rather than as a destination. Hence, we will never get there, but at least it really is possible to get somewhere that is better than where we were before. Of course, it is also possible to get lost whenever we wander into unfamiliar conceptual territory. Our choices on the forked path to enlightenment will either bring us closer to or further away from a functional understanding. Quote, "The universe is under no obligation to make sense to you." Neil deGrasse Tyson. The postmodernist icons of the 1960s had applied a trick that they might have learned from Einstein, whose name had become synonymous with genius. Perhaps postmodernism could do for academia at large what Einstein had successfully done for theoretical physics. The postmodernists attempted to arrive at relativistic conceptions of truth, rationality, and virtue that resembled Einstein's relativistic conceptions of time, space, and motion. In so doing, they divorced belief from objective reality and married it to identity. The postmodernists claimed that reality is socially constructed, but it was a particularly narrow vision of reality that they had in mind. In such a setting, it would be foolish to have either curiosity or integrity, because ideas are to be judged only according to their compliance with fashion trends and arbitrary aesthetic standards. Rather than looking outwards towards nature for confirmation, postmodernists look inwards to culture instead. Quote, "To those who do not know mathematics, it is difficult to get across a real feeling as to the beauty, the deepest beauty of nature. If you want to learn about nature, to appreciate nature, it is necessary to understand the language that she speaks in." Richard Feynman. In the science wars of the late 20th century, the bastions of postmodernism were the so-called soft sciences, such as sociology, anthropology, and cultural studies. Postmodernism went on the offensive as it focused its critical lens on the so-called hard sciences, such as physics, chemistry, and biology, in order to deconstruct them and challenge their claims to objective knowledge. Quote, "Aesthetic criteria are fundamental to the development of mathematical ideas for their own sake, providing both the drive towards discovery and a powerful guide to truth." Roger Penrose. Interestingly, it is often claimed that the main distinguishing feature between the hard sciences and the soft sciences is the presence or absence of mathematics. The defensive strategy of the hard sciences was to ignore and to dismiss the postmodern critiques as fashionable nonsense. The fields of psychology and philosophy managed to stay on the fence in this conflict because it was not obvious which side, if any, they should take. But the main distinguishing feature between these two sides has always been the scale of their preferred level of analysis and the types of structures and questions that they are most interested in. Quote, "We have to remember that what we observe is not nature herself, but nature exposed to our method of questioning." Werner Heisenberg. When skepticism is applied to truth itself, then skepticism loses its foundation, its purpose, and its force. One can understand postmodernism as a consequence of academia focusing its critical lens on itself and becoming self-aware, recursion. One can also view postmodernism as a collection of symptoms that are displayed by a branch of science as it becomes stagnant. The most salient features of postmodern writing are its obscurantism and its frivolity, and therefore it presents us with a subtle parody of academic writing. As its name implies, postmodernism is a mature form of modernism, where intellectual growth continues in the absence of progress. If modernism anticipates an intellectual boom, then postmodernism anticipates an intellectual bust. Once a field of study abandons the goal of enhancing the comprehension of reality, first it loses its purpose, then it loses its moral compass, and then it loses its reputation. Quote, "If my topic is whether or not Vlastos had the best interpretation of Plato's Parmenides, or how the wool trade affected imagery in Tudor poetry, or what the best version of string theory says about time, or how to recast proofs in topology in some new formalism, if I'm wrong, dead wrong, in what I say, the only damage I'm likely to do is to my own scholarly reputation." Daniel Dennett. What people tend to find interesting is ultimately shaped by the pursuit of goals, the most proximate of which is to learn something new. I find it interesting that, over the past century, many of the central concepts of theoretical physics have become estranged from their original and relatively goal-oriented meanings. Particle, information, entropy, mass, work, waste, speed, spin, space, time, simultaneity, curvature, surface, organization, probability, observation, vector, and energy have all changed their meanings significantly since the turn of the 20th century. It is impossible to avoid speaking and thinking nonsense when the most basic concepts that we work with also have such an abnormally low viscosity. Quote, "The mathematician plays a game in which he himself invents the rules, while the physicist plays a game in which the rules are provided by nature. But as time goes on, it becomes increasingly evident that the rules which the mathematician finds interesting are the same as those which nature has chosen." Paul Dirac. Theoretical physics has also been the arena for another science war, that between pure mathematics and empirical science. The stagnation and decline of theoretical physics are, in part, a consequence of the resounding triumph of pure mathematics. The dominance of pure mathematics is particularly evident in the domain of quantum mechanics. Consequently, thinking about quantum mechanics can be very tricky, but it might be rendered amenable to understanding if we accept the following 7 premises. 1. The principle of locality is false. A causal influence may propagate through any frame at faster than the speed of light in principle. 2. The principle of realism is false. Quantum objects such as electrons and photons do not really possess the quantum properties that we ascribe to them, either prior to or after a measurement has taken place. 3. Both hard determinism and superdeterminism are false. Agency, decision-making, and free will are neither binary nor illusory. 4. The concept of probability only applies within a context of decision-making. There is no such thing as mind-independent probability. 5. The concept of information only applies within a context of decision-making. There is no such thing as mind-independent information. 6. Decision-making is the key to sorting out cause and effect. While the temporal order of events gives us a useful heuristic, the application of decision-making through directly manipulating an independent variable is the only fail-safe way to tease apart causation from mere correlation. 7. Decision-making cannot occur in the absence of goals. I understand that some, if not most, of these premises will be difficult for many readers to accept at this juncture, and the relevance of these premises may not yet be obvious either, but sufficient elaboration and argumentation will follow in due course. Shut up and calculate. Origin unclear. I will not be guiding you on an extended detour into the convoluted and esoteric language of quantum mechanics. If the reader is curious about Hamiltonians, Hermitian operators, infinite-dimensional Hilbert spaces, complex conjugates, non-commutativity, non-factorized states, inner products, or Brat and Ket notation, then this book will be of no assistance. Fortunately, it is not necessary to understand the established mathematical language of quantum mechanics in order to understand either the general concepts or the relevant features of reality. Instead, we can directly adduce the empirical observations, and then we can deduce the latent structures that produce these observations, and in so doing, we can effectively circumvent the bulk of the opaque jargon and notation that has accumulated. Quote, "Since the mathematicians have invaded the theory of relativity, I do not understand it myself anymore." Albert Einstein. To be more precise and rigorous, I will introduce new maths below, which will need to be accepted as the absolute axiomatic foundation for everything that follows. Let the first symbol represent the depth of insight contained within a statement, and let the second symbol represent the difficulty in its comprehension. First symbol does not equal second symbol. Both mathematics and natural language are subject to conceptual evolution, and conceptual evolution has the potential to either clarify or cloud the discourse over time. In particular, the mathematics of quantum mechanics have become increasingly abstract over time. Numbers are already inherently abstract, but the equations of quantum mechanics often contain mathematical representations that are more abstract than numbers and are even more abstract than standard algebraic expressions. The problem with such extreme abstraction is that it tends to frustrate and escape genuine comprehension. It has been noted that fear is a loyal servant but a brutal master. Along the same lines, if we outsource our understanding to experts or to mathematical operations, we should do so cautiously and sparingly. There is both a cost and a benefit that comes from applying mathematical conventions to our reasoning. A little bit of dependence is helpful, but a lot of dependence is detrimental. It is one thing to know how to do something, mathematically or otherwise, and it is quite another thing to really know what you are doing. There is also an art to continually retaining our capacity to question and to think independently. If we succeed at this art of thinking, then we can appreciate mathematics more completely, and we can consciously employ the tools and rules of mathematics without entirely losing our minds to math. 3 examples of conceptual evolution. After decades of conceptual evolution, an embarrassing conceptual cacophony has emerged in theoretical physics, and yet the collective mind is focused entirely on the beauty and on the harmony of a system of equations. To briefly illustrate my point about conceptual evolution, the following three concepts have each evolved significantly over the past century. Time. Originally, time was viewed as an independent dimension of reality, but now it is seen as a mere superficial facet of a deeper structure which is called space-time. Time was initially measured by reference to the rotation of Earth, but now it is measured by reference to the oscillation of the cesium-133 atom. Time used to incorporate a wide range of locations in both space and velocity space into a single coherent whole, but now time is broken into localized and discrete units. This means that two different clocks may either tick at different rates or be out of sync with one another, while both being considered to be equally correct. Our concept of time has become more clock-like, less fundamental, and less objectively real over time. Probability. Probability was originally a measure of uncertainty, and as such, it was understood to be subjective, abstract, and dynamic. Currently, in the context of quantum mechanics, probability is treated as if it were objective, concrete, and static. The concept of probability has migrated from a Bayesian and Laplacian notion, which was understood to be epistemological, to an aspect of reality that has gained ontological independence. Probability is now seen as playing a causal role in shaping statistical patterns, rather than as a mere artifact of a statistical analysis, such that probabilities are regarded as more real and fundamental than the actual data that are observed. The line between an uncertainty, which exists only as a consequence of insufficient knowledge, and a possibility, which exists in principle merely because it's conceivable, is also blurred at present. The discovery of statistical patterns that have no known cause or explanation is part of what has driven the conceptual evolution of probability. It is now thought that decisions can be made directly by probabilities themselves, as opposed to considering decisions to be made by agents who are informed by probabilities. It is now implicitly believed that either decision-making in general is illusory, or quantum objects are also capable of making decisions. Entropy. Originally, entropy was defined as a quantity that increases as heat flows from a hot object to a cold object, and as temperatures even out. Now, entropy is regarded as a quantity that increases as time advances and as we require more information to perfectly describe a system. In addition to that, entropy has become an ever-expanding and diversely defined family of related concepts. It is now thought to be true that both time and entropy are directed by probability, such that overall uncertainty must always increase over time. All of these concepts are represented as notation in various mathematical equations, and it will be worthwhile to investigate and evaluate the various assumptions that are baked into these equations, especially given that the equations also serve as the primary means of defining the concepts. It is important to ask ourselves whether or not we still require a dictionary if we have a network of equations and mathematical operations to provide us with all of the meaning and context that we require in order to interpret them correctly. 42. Douglas Adams provided a cutting and insightful commentary on modern thought in The Hitchhiker's Guide to the Galaxy. In Adams's novel, a supercomputer named Deep Thought was able to determine that the answer to life, the universe, and everything is precisely 42. Needless to say, Adams intended the scenario to be satirical, and this particular joke works on multiple levels. Obviously, there is something profoundly unsatisfying about receiving 42 as the answer to life, the universe, and everything. Far from a final answer, this is really the start of a new set of questions. Did Deep Thought really understand our question? do we really understand our own question? Shouldn't we have formed a clear idea of what a reasonable answer would look like before we put this rather difficult and perhaps impossible question to a computer? How could any useful answer be reduced to a single number? These are all good questions that we should reflect on if we are to set realistic goals with respect to progress in the scientific enterprise. It just so happens that 42 degrees is the visual angle of the radius of the rainbow, which is a pseudo-object that has no true size or distance. But I digress. The quantum mechanical context. As this book is about quantum mechanics, I will briefly outline my method for making sense out of quantum mechanics, and for what I think it is about the study of quantum mechanics that makes quantum mechanics both frustrating and fascinating. 1. In order to observe an extremely small system, it is necessary to isolate that system from its environment. 2. Extremely small systems such as atoms are relatively easy to isolate from their environments, but they are also relatively difficult to observe. 3. To the degree that a system is isolated, it also becomes both less predictable and less observable, because observation depends on interaction, and interaction with the system also reduces its degree of isolation. 4. The observation of a system necessarily includes the construction of some representation of that system. 5. Whenever a representation is more detailed than the corresponding system, the causal mechanism behind the details of the representation is broken. 6. The mere act of observing an isolated system also forces a choice amongst alternative potential representations. 7. Failing to understand the structure of the causal mechanism behind a representation causes us to doubt the validity of the representation. In other words, in order to make sense out of quantum mechanics, we first need to consider the interplay between representation, isolation, causality, size, complexity, randomness, and observation. But in order to understand how these concepts are related to one another, we also need to have a firm and clear grasp of what they each mean. If these ideas don't make a lot of sense to you right now, then don't despair, because there is still much that remains to be unpacked. When I first embarked on this project, I had 3 perplexing facets of reality in mind that I wanted to understand better. 1. The elusive and ineffable nature of the irrational and transcendental numbers. 2. The apparently invariant speed of light. 3. The measurement problem in quantum mechanics. The first enigma that I was able to explain was the capacity of the irrational and transcendental numbers to evade description. My success here was very encouraging, and from this experience I came away with an improved understanding of randomness, infinity, information, and probability. This new understanding proved to be very helpful to me as I began working on the more difficult problems. The second mystery that I was able to solve was the apparent invariance of the speed of light. This success was even more encouraging, and it led me to discover an elegant rival theory that significantly departs from the established paradigm of special relativity. With this new theory, I have reintroduced objectivity into the definitions of speed and velocity, and I have restored the original concepts of space and time through applying the crucial concept of velocity space. I have also concluded that light moves in a manner that is radically different from that of both waves and particles. The final challenge has taken me the longest, and it remains only partially completed. Initially, I had suspected that answers would emerge from an effort to sort through and correctly interpret the relevance of and the relationships between the following key dichotomies: infinite versus finite, relative versus absolute, continuous versus discrete, objective versus subjective, abstract versus concrete, latent versus manifest, potential versus actual, fixed versus variable, global versus local, wave versus particle, and analog versus digital. I had a hunch that these would be the deep concepts which would serve as both indispensable tools and clues. I also suspected that my efforts to solve each of these three mysteries would also assist me in solving the other two. A strong synergy seemed evident to me because there is a significant amount of conceptual overlap between each of these three deep mysteries. As I have already mentioned, I am of the opinion that there is no feature of reality or observable phenomenon which cannot be understood in principle. I cannot be convinced otherwise. While my position is a lonely position to occupy, my solitude hasn't deterred me. My stance is considered to be naive and optimistic at best, and arrogant at worst, according to the current scientific consensus. I suspect that this consensus is founded on some combination of learned helplessness and sour grapes, but the best argument in favor of the idea that reality is fundamentally comprehensible is to actually make reality comprehensible. Doing something is obviously an effective way of demonstrating that it can be done in principle. Rather than to waste time with advancing the notion that reality is comprehensible in the abstract, I decided that it would be better to prove this concept with concrete examples. When it comes to our comprehension of reality, knowledge of psychology is at least as relevant as is knowledge of physics. We don't suffer from either a lack of mathematical rigor or an absence of data. What is really missing is an application of psychology because all of the limits with respect to comprehension are psychological in nature. Theoretical physics can and should be rendered psychologically savvy in a way that bolsters comprehension. The tools that theoretical physics relies on, the concepts, the theory, and the language, can all be made more accessible and more user-friendly. A quantum computer functions through the direct application of quantum mechanical insights to computational problem-solving. Meanwhile, artificial intelligence is a direct application of psychological insights to computational problem-solving. One of these novel approaches to computing has borne fruit, while the other has not. But why? This is a good question to keep in the back of your mind. The strange and perplexing quantum realm. Some things are real and conceivable, horses. Some things are conceivable but unreal, unicorns. And some things are real and inconceivable, our subject matter. Quantum mechanical phenomena are often described as weird or spooky because they are both shocking and inexplicable. This psychological reaction stems from an apparent violation of our intuition with respect to the nature of causality. By way of an allegory, I will briefly illustrate quantum spookiness. Imagine that you had attended a Halloween costume party. You noticed that one of the attendees wore a ghost costume and didn't speak the entire time. Nobody in your group knows who the ghost is or who invited them, but everyone has their own theory about who it might be. At some point, the group decides to remove their Halloween costumes, but the ghost refuses to participate, as they apparently don't want to reveal their true identity. Now let's say that after forcibly removing the ghost costume, it was immediately revealed that this ghost was nothing but their costume. There was nobody underneath. This would be a reality-shattering revelation, and it would naturally inspire a number of questions. Through seeing nothing while we are expecting to see something, have we actually seen a ghost? It was in the 1920s that both the Schrödinger equation and the Heisenberg uncertainty principle were first developed. At that time, both the impressionistic art of France and the improvisational jazz of America had already been established in the milieu of theoretical physics. It could have been a mere coincidence, but it is interesting that the quantum mechanical revolution has also inspired a conception of reality that is relatively impressionistic and improvisational. Quantum mechanical phenomena seem to suggest that reality itself is fundamentally impressionistic and improvised. As we probe reality, the deep and stable structure that we would ordinarily expect to find appears to be absent. What appears to be missing is some identifiable causal mechanism that would be regarded as physical as opposed to mental. What if the laws of physics really are founded on the laws of psychology? The study of the theory of quantum mechanics threatens to erode our sense of self and our belief in an objective reality. Not only are quantum mechanical phenomena spooky, but they also present us with a slippery slope that can eventually lead to solipsism. Solipsism is the belief that oneself is the only conscious being that exists, and that there is no real world outside of one's conscious awareness. Reality is conceived of as a mere dream world or as a simulation under solipsism. In response to the looming threat of solipsism, many people will cling desperately to the first argument that makes it possible for them to deny the role of the observer and to affirm the existence of an objective reality. Any ridiculous argument can then become palatable and popular so long as it succeeds in restoring the idea that reality exists independently of consciousness. This is the awkward and conflicted state of affairs that we have inherited from the 20th century. Unfortunately, it is not enough to arrive at the correct conclusion if we have also done so in a reckless or fallacious manner. For example, it is often falsely claimed that only physical interaction, but not conscious observation, is required in order to collapse the wave function, a discrete transition from a wave to a particle. Alternatively, a vast array of coexisting and non-interacting universes has also been proposed, the many worlds interpretation, as an ad hoc means of denying the collapse of the wave function. Elementary particles are also granted the hypothetical role of transmitting information from place to place, as well as the capacity to adopt perspectives and to make decisions. It is often said that the universe has set a limit on the speed at which information can travel through space. And finally, probability itself has also come to be viewed as an entity that is objectively real and concrete, and which exists independently of any conscious mind. None of the above-mentioned notions have been derived directly from the empirical evidence. Rather, these claims follow directly from the foundational and perfectly reasonable belief that reality does not depend on our awareness of it. To the extent that the involvement of consciousness becomes impossible to deny, the characteristics and roles of consciousness are then handed down to entities that would ordinarily be regarded as passive or unconscious. This belief in an observer-independent reality continues to reassert itself in different contexts, but always in a somewhat impatient and careless manner. Ultimately, I do agree that there exists an objective reality. However, rather than to cling desperately to the first buoyant object that floats by, I think that it is better to imagine that we have adequate time to find a viable alternative to solipsism. We do not need to accept solipsism as true, and we do not need to reject it either. Instead, we can take our time and explore all options. Because there is no rush, then we have an opportunity to make sure that our vessel is secure and that it is headed in the right direction before we jump on board. The 19th century roots of quantum mechanics. 20th century theoreticians such as Niels Bohr, Albert Einstein, Max Planck, Werner Heisenberg, and Erwin Schrödinger, are normally understood to be the founders of the field of quantum mechanics. However, I have arrived at the conclusion that the foundations of quantum mechanical thought have actually been established in the 19th century by the likes of Pierre-Simon Laplace, Lord Rayleigh, and Ludwig Boltzmann. It is the overall paradigm that was laid down already in the 19th century that must be identified, challenged, and ultimately replaced. While theoretical physics has benefited immensely from the brilliant and insightful contributions of Laplace, Rayleigh, and Boltzmann, it has also inherited a series of subtle assumptions from them which have led physics down a winding path that leads to nowhere. In what follows, I will be focusing mainly on how Laplace and Boltzmann have oversimplified theoretical physics and created intractable conceptual problems. What is quantized? Discrete variables or dimensions are said to be quantized, meaning that they are not continuous. One can have 3 or 4 water molecules, but not pi water molecules. One molecule can have 3 or 4 electrons, but not pi electrons. An electron can occupy the 3rd or 4th energy level, but it cannot occupy the pith energy level. A molecule can absorb the energy of 3 or 4 photons, but not of pi photons. These are the sorts of quantities that are clearly quantized, but we do not yet know why or how they are quantized, and we do not know what other sorts of dimensions might also be quantized. It is my position that space is not quantized, and neither is time or velocity space. My reason for taking this position is that I have concluded that all contrary views are incoherent. Energy in general is not quantized because, for example, a photon can potentially transmit any amount of energy, depending on its frequency, which is a continuous variable, and because both kinetic energy and momentum always depend on an arbitrary inertial frame of reference. Entropy also cannot be quantized for reasons that will become clear after we explore the history and the utility of the concept of entropy. Spin, or angular momentum, is normally regarded as quantized, but the spin of an elementary particle is fundamentally distinct from the spin of a macroscopic classical object. In other words, the spin that is quantized is not really spin, and the speed and direction of the spin of a planet are not really quantized. This is one sense in which the very concept of spin has evolved over time, and so it would have perhaps been better to have come up with a new term for the spin of an elementary particle, so as to avoid unnecessary confusion. Quantum spin is not literally spin. While it does appear as though both mass and charge are quantized, it is not enough to know that these properties are quantized. We should also have some explanation as to how or why it is that mass and charge have come to be quantized. The most promising explanation for the appearance of quantization in general would be the existence of discrete regions of stability separated by larger regions of instability, but built upon some underlying continuum. The regions of stability would then be the discrete quantized levels that we observe, while the regions of instability would be the gaps in between which are not observed. In this way, it is possible to create manifest discreteness from an underlying latent continuity. The 3 leading interpretations of quantum mechanics. How can an equation be applied if its meaning is unclear, and if there is no consensus on how it ought to be interpreted? According to the consensus view, quantum mechanical theory can be reduced to the following 3 essential equations: Planck's law, the Heisenberg uncertainty principle, and the Schrödinger equation, also known as the wave function. According to this mathematically reductionistic narrative, the various interpretations of quantum mechanics are merely attempts to understand what the Schrödinger equation means in an intuitive fashion. Also, according to this view, there is no need to understand what the Schrödinger equation means so long as we can use it to make accurate predictions with respect to observable variables. However, the accurate predictions that the Schrödinger equation generates are merely probabilities, and so it is difficult to conceive of how this equation could possibly be complete and sufficient as an explanatory model. Where or what do these probabilities come from? How are these probabilities physically determined? How can a probability itself be tangible and real? There is a pronounced reverence for mathematical notation that characterizes physics and sets it apart from the other sciences. Contrary to the consensus that has emerged within quantum mechanics, a scientific theory may or may not be expressed in the form of a mathematical formula, but in either case, a scientific theory is more than just a mathematical formula. A scientific theory is also a coherent explanatory model which necessarily assists us in our capacity to understand how the various observable phenomena that it refers to have come about. I agree with Albert Einstein, Boris Podolsky, and Nathan Rosen, who have intrepidly maintained the common sense affiliated position that the equations of quantum mechanics do not constitute a complete theory. The Schrödinger equation is indeed part of a theory, but a complete theory would do more than just provide us with a way to calculate probabilities. A complete theory would also afford us with some explanation for why the probabilities are what they are. In other words, what we have is merely a concise and convenient statistical description of the data, but what we really need is an insightful explanation for the data. In order to bolster the illusion of a broad scientific consensus, quantum physicists have collectively embraced the idea that quantum mechanics is a singular theory in search of a correct interpretation. But in reality, quantum mechanics is a set of equations in search of a correct theory. Quantum mechanics is really a set of equations without any theory behind them. Could this mean that the universe is actually made of math? Well, not so fast. In various attempts to fill in the obvious explanatory gap, a plethora of competing theories, which are erroneously called interpretations, have been proposed. In what follows, I will briefly outline the three most popular theories, and I will flesh them out with the assistance of a single concrete scenario. The scenario that I have chosen is the infamous single-photon double-slit experiment. To begin with, we have the notion of wave-particle duality. Light is somehow both a wave and a particle because it behaves in ways that are reminiscent of both particles and waves. Due to the wave-like nature of light, if we shine light through a double-slit obstacle, light waves will pass through both slits simultaneously and will project a recognizable interference pattern of light and shadow onto a screen. The interference pattern is attributable to the fact that the waves of the same wavelength can add to each other, constructive interference, or cancel each other out, destructive interference, as their paths cross. Where we have constructive interference, we see bright areas, and where we have destructive interference, we see dark areas. The fact that light behaves like a continuous wave is not shocking by itself, but it does come into conflict with the idea that light is made up of discrete particles. If we send a single photon, a particle of light, through the same double-slit obstacle, then it will manifest as a single dot in the precise location where the photon collided with the screen. What is remarkable about the single photon double-slit experiment is that the location where this dot will appear can actually be described by a probability distribution, which takes the shape of an interference pattern, which is a type of pattern that we know must be created by waves. The light areas on the screen now correspond to areas where the single photon is more likely to land, and the dark areas on the screen correspond to areas where the single photon is less likely to land. Intuitively, the best explanation for the observations appears to be that the single photon traveled through both slits as a wave. It then constructively and destructively interfered with itself, as though the two slits were themselves sources of light, and then at the moment when these interfering waves interacted with the screen, a specific location for the photon collision site was selected randomly from all possible locations. And this location was also constrained by the probability distribution that was determined by the interference pattern. So the wave creates the interference pattern creates the probability distribution, and the location of the collision site is determined randomly in such a way that it statistically conforms to the probability distribution. Now, what are we to make of this? The Copenhagen model. According to the original Copenhagen explanation, the photon begins as a wave, which then transitions into a particle at the moment that it comes into contact with a photosensitive screen. This transition is known as the collapse of the wave function. This idea of wave function collapse at the moment of observation leaves us with the following difficult questions. Why would a wave disappear and be replaced by a particle? How would a wave disappear and be replaced by a particle? How does the act of observation cause a wave to transform into a particle? The many worlds model. According to the many worlds account, the wave never transitions into a particle because the observer actually splits into billions of identical observers, and each of the billions of possible collision site locations is actually seen, but each by a different observer. These billions of observers would be the alternative future selves of a single original observer. So the wave is a coherent whole which comprises billions of particles which are each individually seen by billions of separate observers. If we consider these billions of observers together as one, then the wave still exists, in some abstract sense, after the particle has been observed. The reason that we cannot empirically confirm the existence of these billions of other observers is that each observer also gets their own identical universe. And so there is a one-to-one correspondence between observers and universes. We are not able to interact with these other universes, and they are not able to interact with us. Hence, the idea has been dubbed the many worlds interpretation of quantum mechanics. According to the many worlds theory, the precise location of the photon particle is not defined prior to observation, nor is it defined at the moment of observation. If the precise location of the photon particle ever becomes defined at all, then this must occur at some time after it has been observed. But it may also remain undefined indefinitely. Meanwhile, the wave never actually disappears. It merely divides into billions of particles. But why should each observer inherit their own isolated universe? Isn't it convenient that there is no possible way to verify the existence of these billions of universes? Why did I end up as one particular observer amongst billions and not another? Does any physicist genuinely believe in this theory, or is this all just an elaborate prank? It is difficult to explain how the location of the collision site of the photon on the screen is decided. With the many worlds theory, the decision as to precisely where the particle will land on the screen has been deferred, but the decision as to which one of these billions of observers will become my actual future self cannot be deferred. This decision must be made somehow, and this decision is just as arbitrary as the decision as to where the photon will land. One could try to dodge this question again by saying that all of these billions of observers have an equal claim to being me. Implicitly, then, the question as to which one of these future selves I will be can be regarded as misguided, because I will be all of them. But yet it still remains true that I will not experience reality through the perspective of all of these observers. Instead, I will only experience the reality that one of these observers observes. Hence, I will only see the photon land in one particular location on the screen. In this context, the meaning of the term I becomes ambiguous. Can all of my hypothetical future selves be described with a single I? But a little common sense can go a long way to restoring clarity. For all of the extravagance and peculiarity of the many worlds interpretation, it has gotten us nowhere in terms of progress. Despite our desperate attempt to avoid answering the question of how this arbitrary selection mechanism works, this original question still stands directly in our path, albeit in a slightly different form. How and why is a particular collision site selected from amongst the billions of hypothetical possibilities? How is the apparent direction of the motion of the photon decided? The pilot wave model. According to the pilot wave theory, the precise direction of the photon is already defined prior to observation. What happens according to this view is that each photon particle rides on the waves like a tiny surfer, and this dynamic somehow produces an interference pattern on the screen. Hence, the waves only exist as a mechanism that steers the movement of the particles. In this account of the single photon double-slit experiment, the wave never disappears, but it also never interacts with anything directly, aside from itself and the photons. Pilot wave theory is what is known as a hidden variables theory, and as such, it appears to have been refuted by more advanced versions of the double-slit experiment, as well as by attempts to experimentally verify Bell's inequality. Having said that, the correct manner of interpretation for the various experimental observations as they pertain to interpretations of quantum mechanics is also the subject of endless debate. The core difference between the three leading theories of quantum mechanics is that they each supply a unique answer to the question of when the location and the direction of motion of the photon become defined. Pilot wave says that the location and direction are already defined prior to observation. Copenhagen says that the location and direction are defined at the moment of observation, and Many Worlds says that the location and direction remain undefined after observation, and are perhaps never defined. As a result of these different solutions to this single problem, each theory has evolved in a different direction and assumed a different shape. The many worlds theory becomes relatively convoluted, because it has the additional burden of explaining how these particle properties can still appear to be well-defined if they aren't really well-defined. Another possibility to consider. What if the appearance of the photon is just an illusion? What if no particle ever exists? The photon seems to have more in common with a spontaneous lightning strike, or with the localized rupture of a bubble, than it does with a grain of sand. The photon might be akin to an overflow of excess energy, perhaps the result of a discharge from an oversaturated container. The particle that is detected through absorption may be an entirely different entity from the particle that is emitted. But why does the energy transfer appear to occur in a specific location and at a specific time? Why does the amount of energy transferred depend on the frequency of the light? How are these localized discharges of energy produced by a wave?